And I think we should probably get started. Hello, everybody. Thank you for joining. May 15, I have the pleasure to introduce Tom Nicholas from Earthmover. He's a forward engineer, and he's essentially kind of like spearheading this virtualization effort within Earthmover. I guess the community at large, they're interested in this, especially from a lot of people who use NetCDF, HDF type of data sets. Welcome and thank you again. Tom, whenever you're ready, you want to start, this is your floor. Leave it up to you.
Great. Thanks for having me. Um, yeah, my interest in virtual chunks actually predates my employment with Earthmover. Like when I worked for this nonprofit Seaworthy, I realized this was like an important unsolved problem and started working on it there. But today I want to talk at a quite a high level and kind of step back and kind of talk people through like what we even mean when we're talking about virtual chunks and what kind of why this is a useful concept, how this manifests itself. There are these like abstract concepts that manifest themselves across multiple different software libraries, and that's kind of the perspective that I wanted to give in this talk. Um, and the title comes from the fact that recently the usage of virtual chunks has kind of gone from this curiosity and this clever trick to something we actually use quite a lot within Earthmovers, both open source and products. Um, this is also the first time I tried using Claude to make some slides with slide dev, so let's see how that goes. Okay, so what I want to cover is firstly just like why we even talk about virtual chunks, like why does this come up? And then get straight on some key definitions, like what do we mean when we talk about a virtual chunk? What is a chunk manifest? Why is that important? And then this lesser talked about, but similarly important one of a virtual chunk container. And these things often have different names in different contexts, but are fundamentally the same thing. Then I want to talk about two specific implementations. One being Icechunk and how Icechunk manages these concepts, and also how the VirtualiZarr library manages these concepts. And then I want to do a more general comparison of manifest formats across a range of libraries. And then finally, if we have time and people are interested, I can talk about some considerations for like real world production usage that I had to think about recently within the context of the Earthmover platform and both things that are enabled by virtual chunks, but also things, additional considerations that come up, that things you have to worry about when you have virtual chunks that you don't have to worry about if you don't have virtual chunks. So, firstly, like why are we even talking about this in the first place? And stepping back a long way, like to just like what are the properties of object storage itself? For the purposes of science, object storage has two main important properties. It makes it very easy to access data from basically any location because you are allowed to fetch the data from anywhere, not just on the same HPC machine, not just on the same file system. We're going to ignore the fly in the ointment of egress fees here, but in general, like that's the promise of object storage. But um, unlike a file system, object storage makes it very hard to change the data once it's written because there's no ability to edit just part of an object. You can only overwrite the entire object. And there's not even a move or rename primitive in object storage systems. If you issue a move request to S3, it will actually create an object with a different name and the same contents, then delete the original one, which is slow. And so you can think of this as like object storage is kind of a write once, read many system. Um, and from that perspective, then having some kind of primitive for referring to data at rest is kind of like a natural thing that you might want in the context of a system where it's easier to read data than it is to write or update it. So when we talk about virtual chunks, like what specific abstractions are we actually like talking about? The first and most important one is obviously a virtual chunk itself, like a single reference. And by that, we mean a lightweight reference. You can think of it like a pointer to a single object living in an arbitrary storage location. It's always a single contiguous byte range because object storage supports HTTP range requests, and you can't do a range request across multiple objects. That would have to be multiple range requests. So it needs to be a single contiguous byte range. And that those bytes might live inside any object, and those objects might also be known as a HDF5 file or a netcdf file or a group file. Could be an object storage, but you can also do this on a file system. And so you can think of this reference as a tuple of a URL or a location string, and then a byte range specified by the start and end, or the start and the length, the offset and the length. And so this points to bytes that already exist somewhere else. And this is purely a storage optimization. It's like it's kind of like an external table in like SQL database land. Um, which means that it lives at the I/O layer, not the data model layer. Like there's nothing here about Zarr specifically or tables or anything like that. This is lower level than that. Um, which means that because it's purely an I/O level concern, it's completely orthogonal technically to things like the Zarr specification. Like it has nothing, like Zarr doesn't know about this and shouldn't know about this, because this is just implementation details of how underlying bytes are fetched. Um, the second key concept we've got is the manifest, the chunk manifest. So what do we mean by that? Um, What we mean is the thing that maps the logical data model, e.g., like groups, arrays, shapes, or if it was tabular, like tables, the thing that maps that model to the chunk references, like where are we actually going to get the bytes? So in Zarr, your data model might say, I want the chunk that's under these indexes, like the second chunk along the first axis, etc., of the array named temperature, and then it consults the manifest to translate from that key to, okay, I need this specific path and I need this byte range. And so in the context of like databases where there's this nomenclature of like a logical layer and a physical layer, the manifest is the mapping from the logical layer to the physical layer. And it turns out that this is a super useful abstraction because if you clearly separate the logical layout and the physical layout, you can change one of them independently of the other. So if you want to make changes to the physical layout, that might be swapping out a virtual chunk for a native chunk or vice versa. And the Zarr structure on top or the tabular structure on top in the logical layer doesn't even have to like know that you've done that. Um, or you can make changes in the logical layer without changing the actual physical layout of bytes. So for example, I can rename, if you have this separation, then you can make changes such as renaming or moving around Zarr groups only by manipulating the manifest, not by manipulating the actual chunks on disk, which is generally like millions of times less expensive because the manifests are millions of times smaller than the actual data they are pointing at. And this ability, this splitting is like, I'll come back to this, but this splitting is like key to how Icechunk implements most of its features. The manifests themselves contain various different types of chunks. And so we've talked about virtual chunks, native chunks, but really in general, there's like four types. There's a virtual chunk, which is some arbitrary byte range and some arbitrary location external to the kind of storage that you have the authority to edit. Then there's what we think of as normal chunks, native chunks, which is just a single object in object storage contains a single chunk. If you put multiple chunks inside a single object on S3, which sometimes it is like advantageous to do, we might say that that is a shard. Different systems use chunks and shards in different ways, but generally, like multiple things inside one object, someone's going to use the word shard. If the chunk is absolutely tiny, like say it's just a single scalar, then maybe you just shouldn't bother having a separate object at all, and you should just put those bytes inside the manifest itself, and then it's an inline chunk. Um, and the choice between these is again, it's a purely like physical layer, purely storage layer choice. And whilst I'm using the nomenclature here of like Icechunk and Zarr, this idea is not unique to Zarr at all. And so, just to pick another random example, there's a startup called Lance, which has this file format called LanceDB, which was somewhat influential on Icechunk's design. It's different because it's tabular and it's different in a bunch of other ways, but it is similar enough that like I just pulled this image from one of their blog posts, and this has inline packed, which is really sharded, dedicated, which is really native, and external, which is really virtual. And they have exactly the same splitting. So really, you should think of this like splitting as just like a natural consequence of what happens when you design a storage system from the ground up for the properties of cloud object storage. The final concept that is useful like across implementations has the least clear name. In Icechunk, it's called a virtual chunk container. In Lance, it's called a location base. Some libraries don't really have it and then suffer for it. But there's this general problem of like, okay, I have billions of chunks, and in general, they're in completely different locations. But in practice, they're probably like mostly in one location. Like I have billions of chunks that refer mostly to the contents of a single bucket, or maybe like two buckets. Um, and it's very useful to have some kind of concept that helps you group the co-located chunks. So you might want to use a prefix. You might want to say, okay, um, um, this this store contains many virtual chunks, but all of them live somewhere within this prefix of this bucket. And we would say that that is the virtual chunk container. Um, and the reason this is so helpful is because then you can start to reason about the different locations of the data on a per bucket basis or a per prefix basis rather than a per chunk basis, which means if you're worrying about things like, oh, does the user have permission to read from this bucket? You can do that once just at all rather than once per chunk, which is potentially like millions or billions of times less often. So it's very useful to have this concept. Um, and there's no reason why a single data set can't have multiple virtual chunk containers. Maybe there's some data in S3 and there's some data in Google Cloud, and they're still considered to be part of the same logical data set for some reason. But at least then you're only worrying about two locations to track rather than a billion locations, half of which happen to be one and half of which happen to be the other. And again, Lance has a concept for this. Databricks' Delta tables have something similar. But Icechunk calls it a virtual chunk container. So that's kind of the third sort of foundational concept here. Um, so let's talk about some examples of how this gets expressed in particular implementations. And I can't see any chat, but if people are, if this none of this, if this isn't clear to people, then please send questions. I'm specifically going to talk about Icechunk and VirtualiZarr, two systems that I've been heavily involved with. Um, so Icechunk first. So how does Icechunk express these concepts? So Icechunk has chunk references, which can be inlined, they can be virtual, they can be native. And then it has these manifests, and it stores these manifests on disk using the flat buffers format. And they're split or paged into individual manifest files. So a single Icechunk store can have an unboundedly large number of manifest files. Um, and then each version of the data corresponds to a single snapshot. So the store contains snapshots for each version, and the snapshots contain one or more manifest files that track the locations of the actual chunk objects. So there's kind of this like triple hierarchy. But this is a very powerful layout because it means that each version, each commit can be interpreted individually. The fact that the manifests are split up means that you can have essentially like arbitrarily large data sets, very large numbers of chunks, fairly large numbers of manifests, all referred to by one snapshot. Um, And then when you want to fetch the data, you only need to fetch the manifests that are actually relevant to the region that you're reading. Um, yeah. Icechunk also, when you write new data, it doesn't need to write new manifests. It works out whether or not a new manifest would be required. And if it's not required, then it doesn't write a new one, which means and the same thing is true of the chunks. So if you have like a petabyte size array and you only changed one value, you would only need to change the one chunk that contains that one value in your second version of that array, and you only need to change the manifest that contains the reference to that chunk. You don't have to change like all the other manifests that contain the references to all the other chunks in the array. And finally, it has this lesser known but quite useful feature where one of the downsides of a virtual chunk is that obviously if you create a reference to someone else's file, you can't stop them changing that file. And then if you try to fetch bytes from it, you might get anything. Um, but what Icechunk does is it stores the last modified time of the file. So at ingestion time, it records when the file that its reference points to was last changed, so that then at runtime, when it reads it, if it suddenly sees, hang on, that file has changed more recently than I think it should have done, it can fail loudly and say, okay, you're reading like unsafe bytes here, like this could be anything. Um, Whereas if you don't do that, you could sort of get silently corrupted data. And in fact, this splitting is done quite neatly. Like this is literally from the Rust code in Icechunk, from the part of the code that like reads the format. And you can see that there's this enum, which has three different types for inline chunks, virtual chunks, and this is one is for native chunks. So this splitting is just done at this like very low level, like all of Icechunk's machinery, and then finally, right at the end, when it goes to actually fetch the chunk, then it sort of consults this and works out which type of chunk it's actually fetching. And this design is pretty cool. Like this has a lot of nice properties. Um, it's scalable because of this splitting of manifests that I've discussed earlier. Um, it's efficient, this deduplication. The fact that we have virtual chunk containers as a first class concept means that we can manage the prefixes of different storage locations in a tractable way. And it has a nice separation between the physical layer and the logical layer, which is what allows you to do things, types of operations that would be very hard with native ZAR, but are very easy with Icechunk, such as shifting an array sort of like left to right or along an axis, or moving or renaming an array or group. These become very cheap because they're manifest only operations in Icechunk, whereas in ZAR, you would potentially have to rewrite every chunk. In native ZAR, you'd potentially have to rewrite every chunk to be able to achieve those operations. And interestingly, nothing about what I've described here is really specific to the ZAR interface. Like the Icechunk files, like the manifests, the snapshots, the chunks, they don't really know that they represent the back end to a ZAR store. The ZAR interface and the Icechunk like ZAR store kind of object like API on top is quite a thin layer on top of this more general system underneath. Like in theory, it would be possible to have to store like tabular data in Icechunk and provide like a Parquet-like interface or something like that. Um, okay, that's Icechunk. VirtualiZarr is quite different with a quite different scope. So instead of being about storing files on disk and versioning them and all the rest of it. VirtualiZarr instead is an in-memory tool for extracting and organizing and collecting together virtual references. And so instead of being it doesn't have an on-disk format. It's an in-memory array of chunk references, and it has a concept of a manifest, but the manifest is actually just like a Python object that is a multidimensional array. And each element in the array corresponds to one entry per chunk in the logical grid, where the grid is the grid of ZAR chunks. So each entry again has a path, an offset, and a length. Um, and you basically like literally under the hood, it's just like a set of NumPy arrays that store this information. The manifests are in memory, but part of the point of the library is that they can be written to or read from various other different, like more permanent storage formats for these references. The whole point of VirtualiZarr really, or at least the reason why I originally designed it, was that um, I saw people trying to manipulate references to files in a way that made much more sense if you thought of the files as arrays of chunks. And so the manifest is literally in VirtualiZarr, the manifest is literally a multi-dimensional array in the sort of Python duck typing sense. So it understands what it means to be concatenated with another array or be indexed into. And the nice thing about that is that then you can wrap it with Xarray and use Xarray operations as your sort of lingua franca for joining lots of data together. Um, and virtualize manifest arrays, it's designed in such a way that you can have an array of virtual references next to an array of just like normal in-memory chunks, and it's quite happy to handle both. But all of this is very tied to the Zarr data model. Unlike Icechunk, the assumption that we are dealing with a regular Zarr grid of chunks is baked in to virtualize Zarr, and hence why Zarr is like in the name. Um, and so it is really completely tied to the concept of a Zarr data cube. The whole point of it is to make it easy to assemble these data cubes. VirtualiZarr also has these parsers, so it's an extensible system of it's like an extension point that allows you to read virtual references from various different file types. And when we read these references, we have to scan the contents of the file, but we also are trying to map the contents of that file to the Zarr-like model. So you take what's in the netcdf file or TIFF file or whatever, and then you say, okay, if this were a Zarr store, what would it look like? And that's the other thing that these parsers do. Um, and the parsers are quite flexible, and you can write your own parser. But the limitations, the fundamental limitations are that we're assuming a Zarr data model, so you have to you can only pass into things that can be passed into the Zarr data model. Um, and also, we are assuming that every chunk maps to a single contiguous byte range. Um, because if it can't be, it's not possible to access it efficiently on object storage in general. And there are some file formats that don't meet this requirement. They sort of split data up across the file in a weird way that invalidates this, and those just like can't be efficiently like virtualized. Um, the final thing that VirtualiZarr does, or that people are sometimes not aware of, is that you can actually read data directly using VirtualiZarr if you want to. Like normally the use case is parse a bunch of files, concatenate them all together, serialize the result to Icechunk. But actually you can, if you want to, you can just read directly from that data. So for example, if I call a TIFF parser on some cog or whatever, I get this object back that is a valid Zarr store that can be opened directly with Xarray and loaded, this manifest store object, um, which is kind of neat. So in a sense, it's like providing this kind of like universal API over multiple different file formats, mapping them all to the Zarr interface. Another thing it does that's useful to make explicit here is that like it does have a mechanism for tracking common prefixes. Like it has this object store registry object, which kind of looks like boilerplate when you use it, but it has a purpose, and its purpose is similar to the virtual chunk containers. It tracks like which prefixes, which buckets we actually care about here. And as the author of VirtualiZarr, I kind of see it as a useful but potentially transient tool. Like the whole point of it is to make it easier to assemble these references on disk. But it was made because there wasn't like a super easy way to do this. And I think at some point in the future, then we can probably do a lot better and have some much more integrated tool that doesn't require its own entire standalone library to do this. Um, yeah. So if we think about these different concepts that I've introduced and we compare them across um, different implementations, then you end up with a table that looks something like this. Now, my confidence and level of knowledge drops off sharply as you go further right on this table. So I've almost certainly got something wrong over here. So please don't be offended if I've accidentally like misrepresented your favorite piece of software. Um, but in general, you can see that like the other Icechunk is like on par with these other like tabular industry leading software solutions in this in the number of features and the number of things that it considers as a first class concept, in its scalability, in its protection against different types of safety. Um, VirtualiZarr is kind of in an odd category because it like some of these considerations just don't apply because it's this like in-memory structure. Um, but and then Kachunk is just missing several key features, such as the prefix mode. Like, there's no equivalent of a virtual chunk container in Kachunk, as far as I know. Um, and then DMR++ is like designed with a different context in mind. One of the most important ones being this serverless data access. Like, if I understand correctly, if you wanted to load data directly, the intended way to load data from a DMR++ file, and please correct me if I'm wrong, is via a hierarch server, and the server needs to be running. Whereas with Icechunk or even with Kachunk, the idea is that the client is able to be given the authority to go and read bytes directly from S3 without consulting a server. Um, yeah, so I thought that might be an interesting point for discussion. Um, how long have I been talking for? Okay. How is this making sense to people? Like, do people have questions at this point, or are we happy for me to like talk about ways in which we use this? Okay,
Yeah,
Christine, give me a thumbs up, and so
I
is
was,
that.
yeah, Tom, like this is great. There's some questions, so it's up to you if you want to address some questions. So we can also leave them towards the end. Keep it with the flow of the presentation, and then we'll just revisit the questions. It's up to you. You decide.
Um, I think I'll come back to these questions. I think they're all good questions, but I don't think any of them prevent talking about the next slides. That makes sense. Um, cool. Okay, so I just wanted to give some kind of teasers as to ways in which we have recently been using virtual chunks in Earthmover. Um, so this is just two like interesting use cases. So one is we have this requirement for like embargoed or time windowed access to data. And one way to do this efficiently is to use virtual chunks. You can basically have like a private version, the private part of the data set and the public part of the data set in different locations and use virtual chunks to have one refer to the other, and then use sort of authenticated and credential management solution that in this case is Array Lake to gate access to the embargoed part to only people who have authority, but make the entire rest of it public. Um, and this is quite useful in the context of like weather data commercially because it allows data providers using Array Lake to do things like sell like very up to date, low latency forecasts, but then keep a public archive of the data that is older than like a few hours or something. And you can use virtual chunks as a mechanism to set a system up like this and do it without having to like duplicate or copy data around. You just kind of like put it in these places and change like the chunks, the references that refer to it or the authentication on the references that refer to it rather than moving the actual data. And then very similarly, We have a blog post here about what we called filtered subscriptions, but it's basically a similar idea, but instead of like gating on uh, time within along an axis of a data set, we can gate on other things like which variables. So this allows like one commercial data provider to sell different subsets of a cloud native data set to other consumers, depending on like what that specific consumer pays for. And you should read the blog post for like the description of exactly how this works, but this works using virtual chunks. Like essentially what we do is we subscriber A gets given a manifest that contains like virtual chunk references to only the data that they have paid for. And subscriber B gets a manifest that contains virtual chunk references to only the data that they have paid for, which might be completely different or might partly the same or whatever. And this is done in a way that allows the original provider, like the seller of the data, to only actually have one copy of it. And that was a need that we saw was just like not really being met by other solutions. So that's kind of a cool use of the virtual chunks as well. Um, Final section is on this kind of rabbit hole that I went down over the past few months of just like security considerations. So virtual chunks are extremely powerful, but they're also kind of dangerous because they're a reference to an arbitrary location, and that location can contain arbitrary data. And so there's a few things that could hypothetically go wrong in a system that's using virtual chunks. So one is like exfiltration of sensitive data. So imagine that some bad guy creates a manifest or a Icechunk store with a manifest or something like that that has a virtual reference like file, so local file path of whatever machine this is being run on. And let's say it's like Tom's PC, and then he's like written out the Bitcoin wallet or AWS credentials or something like that. Um, because our virtual chunk system will happily read data from this location if it is able to. All he then has to do is say like, "Hey Tom, load this like dangerous Icechunk repo and send me back the results." And I could unwittingly use Icechunk or VirtualiZarr or Kachunk or whatever to load the bytes that make up that file, like the contents of the Bitcoin wallet. And then if he can somehow convince me to send the results without me realizing what I'm doing, then he's found a way to basically like exfiltrate arbitrary files from my machine. Um, Another class of security problem is just like overexposure. Like if a virtual chunk container refers to like a whole bucket, and you give someone permission to read from that virtual chunk container, like you've effectively given them credentials to read from your entire bucket, or at least the specified prefix. And so if this isn't managed carefully, you could imagine some scenario in which like imagine some intern at a bank or something like tries to use virtual chunks for something, but doesn't really understand what they've done, and they've accidentally just like exposed all their company's like most private data in a bucket to people that should never have had access to it. Another like kind of less important problem is just like the whole problem of someone overwriting the data that you're referring to. And I mentioned this earlier, Icechunk does have built-in defenses against this, where if the data has been changed, you know that at read time, but it's kind of in a similar category of problem. So raw open source Icechunk defends against these by requiring you to explicitly opt in to any virtual chunk container. That's why you have to pass this like authorized virtual chunk access keyword argument, which is good in that it's safe. Like it forces, because then the user would have to say authorize Tom's like Bitcoin wallet or whatever. And if they type that in and press enter, then like to some that's like on them at that point. Um, But the problem with that is that that's a pain for users because now users have to like manually authenticate to the locations they're trying to read, and they don't necessarily know what locations they're trying to read if they're reading some like data set that they've only just heard of. And it's not super user friendly, but you can't really make it more user friendly and more like magical without making it more dangerous, at least with this like pure OSS serverless design. Um, but if you do have a trusted server that is handing out the credentials, you can do a lot better. So in the context of Array Lake, we are able to solve this problem quite neatly because Array Lake, in the same way that like GitHub servers do, it tracks its users, it tracks their permissions, it tracks what storage they are meant to have access to. And so it's able to basically validate and keep track of virtual chunk storage locations like the virtual chunk containers and make sure that they are safe and make sure that people are only able to access the ones they're supposed to. And our app is able to layer as many additional kind of like, are you sure messages or whatever on top of that to protect against accidental overexposure. So if you use Icechunk with Array Lake, you get this like nice magical experience where you don't even need to know that you're looking at virtual chunks. The user just opens the repository and it's like, oh great, I've got access to this data, whilst it is still safe because various other checks have been done either before when the data was made or behind the scenes. And I have a blog post I'm writing about like the details of this, but I thought that might be interesting as well. Okay, so at the end, what did we learn? Recap. Um, I think the main points I want to get across are just like this virtual chunk thing is not really just like a niche concept. It's kind of a natural requirement for systems in object storage. Another important takeaway is that this is really an I/O layer concern. It's completely orthogonal to the Zarr specification because it's like physical layer versus logical layer. I think Icechunk's implementation is really cool. Like I wasn't the one that designed it. It was this guy, Sebastian Galkin at Earthmover, but he deserves a lot of credit because there are a lot of very like far-sighted design decisions. But these core ideas are partly inspired by other systems out in the world. And I think that once you have these virtual chunks, then you kind of start to realize that there's lots of interesting things you can do with them, maybe that you weren't anticipating, such as these filtered subscriptions I mentioned. But the downside is that like there are serious security considerations, and I don't think that these security considerations in general are fully solvable without some kind of trusted server dispensing the credentials. Um, yeah. That's the end of my talk. Thanks for listening. Happy to answer questions.
Yeah, great talk, Tom. Yeah, this is great. Let me turn. So yeah, we have a few questions here for you. I can read them, or let's say James Gallagher asks about indexing, and I think it was in Icechunk you were talking about indexing,
Hmm.
and the question was whether this indexing was just spatial or more flexible, or
So I mentioned that Icechunk exposes this Zarr interface, but the Zarr interface is quite thin. So the intended way to use Icechunk today is through Zarr indexing, right? You index into the array or you ask for a specific chunk, and that indexing is done in like Zarr array space or Zarr chunk key space. And so in that sense, it's not geospatial, it's just what Zarr is, which is kind of arbitrarily multidimensional arrays. Um, in theory, it might be possible to build other interfaces, indexing interfaces on top of it, but that's how it works today.
thank you. I think Ethan had a related question. Ethan Davis says, he says, perhaps related to this question, does any data set metadata, HGF EOS or any CF, get elevated up to the chunk manifest level of indexing? And if you want to if you want to add to that, Ethan, you're welcome to unmute yourself.
Yeah, I think it's. Can you hear me? Yeah,
Yeah, yeah.
yeah. I think it's related to the indexing, the geospatial indexing James asked about. It's just really, is there, and it doesn't seem like it would be from your last comment. I think it would have to be a layer on top of that indexing into the actual geospatial stuff. So that's, I think you kind of answered that with your last one. It just would reflect, you might, yeah.
Yeah,
So
yeah.
I think there's
So
certainly cases where that would be really important and helpful, and there's probably, I think, a number of implementations of things that aggregate at that level and have tried to do that. So it might be something to think about as a layer above kind of the chunk manifest that these meetings are about. But I think it might be really interesting at some point to talk about that more. Anyway, thanks, Tom. Great presentation.
thanks, Ethan. Yeah, I kind of see Icechunk as a pretty generic storage system. Like it's generic to just like bytes at a low level, and then the Zarr store interface is generic to arrays, which may or may not be arrays that represent netcdf files, or they could be something completely different. Like my background is in plasma physics. Like I do not think of all arrays as being netcdf like CF conventions. Like um, there's no reason why you couldn't put like biology data in. I mean, but really here we're just talking about the properties of Zarr rather than the properties of Icechunk, right? And so from that point upwards, we just get back into the same sort of like discussions around Zarr conventions and all the rest of it that we're used to. Like Icechunk just slots in underneath all of that. In theory, you could push more information down into the chunk manifests. Um, but I think, and there are arguments to do that. Like, for example, one of the things that I'm kind of need to do soon is um, start pushing aggregate storage metrics like total chunk sizes and stuff down into the manifests. Um, but I kind of think it might be a mistake to push like geospatial specific conventions down into the manifest files themselves, because then you've broken this nice like abstraction layer. Um, I would prefer to see that on the top as like a Zarr convention, for example.
Yeah, that's an interesting point. Yeah, at the top level. Yeah, thank you both, Tom and Ethan. Anybody else has another comment about related to this indexing, geospatial indexing? Or otherwise, I'll move on to the next questions.
So there's one here about how do Icechunk or VirtualiZarr handle chunk compression and encoding. So the
Yes.
answer is like because the virtual references refer to chunks as they are and they do not edit the chunks, then we simply inherit however the chunk was compressed or encoded. So in order for VirtualiZarr to like pass the contents of a file, it needs to be able to say, okay, this TIFF file or this GRIB file used some codec for encoding, and I need to like write down that it used this weird codec in my Zarr metadata. And Zarr has flexibility with respect to codecs, which is good because it means that the set of possible file formats that you can virtualize becomes much larger. Um, but it can be a pain that it's like possible for someone to define a third-party codec and then be like, yes, you can read my data, but only if you install my codec. It's kind of trade-offs there. Does that make sense?
Um,
Yeah. Well, yeah, James, you want to add to that? Yeah.
yeah, it makes sense. So neither actually decode the chunk. They simply pass on the meta information about how to decode it.
Exactly. So again, this comes down to like logical versus physical layer.
Yeah,
Like
sure.
the physical layer is like, okay, I need these bytes. And then it's the responsibility of the logical layer to actually decode the contents of those bytes.
Right, right. Yeah.
Uh,
Yeah. So I guess it's kind of related. Maybe you already answered, but I was thinking because I've also been kind of like dabbling into VirtualiZarr and like this idea of generating these like aggregated virtual references for at the collection level.
Yeah.
And that's something that didn't, and it's unclear to me, and maybe maybe you already answered, maybe it's still, maybe it's already clear for everybody. But in the case, say, for example, you have many different files, but at some point, either the endianness of the file changes or the compression level,
Right.
kind of this kind of encoding changes. And is that something that it's kind of like supported? Um,
So
or sorry, or within the same file, for example, same array may have like a chunk that has a different encoding than a different chunk. So those kind of like scenarios are ones that I'm thinking
yeah,
of.
yeah. So from the perspective of the physical layer is ignorant of these details. Like the physical layer just fetches the bytes and it doesn't know that like the bytes from one chunk were encoded with one endianness or whatever. Um, but you still need the logical layer to decode it. And then the assumptions of the logical layer can start to become problematic. So um, at the moment, our stack for virtualization assumes the Zarr data model, right? Like VirtualiZarr assumes that, and Icechunk's interface assumes that. And so, although it's possible to create virtual references to two different chunks with different encoding, there's no way in the logical layer right now to tell Zarr that you have one array that contains chunks of different encoding. And so at the moment, that's a limitation, but it's technically, arguably, a limitation of the Zarr data model rather than a limitation of like the virtualness in general. It just and actually like you could encounter this problem even without doing anything virtually. Like if I'm making a big Zarr store and I write the first half of the array with one codec, and then I decide, oh no, actually, there's a better compression codec I could have been using. Let me write the second half of this Zarr array with that codec. So you can't do that either, even though that has nothing to do with virtual references. Like you can't do that either because you're violating one of the properties of the Zarr model by doing that. Um, it, the, it's just that this comes up more often in the context of virtual ingestion because it's kind of funny. It kind of forces you to confront the inconsistencies of the data that has been written in a way. But it can be quite frustrating, and it's definitely one of the main downsides of how this works, at least currently. I have had some annoying experiences where you look at a massive archive of files and you think like, great, this is all one massive data cube, and then you realize that actually no, the first half of Go's used one compression codec and the second half of Go's 16 used a different compression codec. So the best I can do is two separate arrays, even though logically they should be one. Um, but I see this as something that like could be improved with extensions to Zarr or some other clever solution in future. It's not insurmountable. Um,
Yeah, that makes sense. Yeah, I've seen something similar to as well, and it's just frustrating overall, no matter what. Yeah, thank you. Um, Anybody have a follow-up on that, or I'll just move on? I think we have one last question, but I see Ethan raise his hand. Micah,
I was
um,
just going to say, can I ask now, or sorry, were you going to say something else, Miguel?
is this a follow-up to the encoding, or is this
Yeah.
okay?
Well, I think it's a kind of a follow-up to the aggregation kind of comments that
Oh,
were just.
yeah, yeah, sure, go. There's one last question from Christine, but yeah, sure, you should go, Ethan, and then I'll read Christine's question.
Okay. I was just going to say, I think that's one of the things we saw when we were doing aggregation was that over time grids can change, and I think that's kind of where the need for geospatial indexing information being elevated comes in, because then you can kind of think of it in terms of geometric, I mean, any spatial geographic, what am I saying? Yeah, coordinates, and that can help simplify some of those heterogeneity issues that you see across time or whatever with different models and things. It's, yeah, it's a pain in the neck, but that's what data is, I guess. Anyway, sorry, just a comment. Thank you.
Thanks. Micah, did you want to add something to that? I'm curious.
Yeah, hi. Hi,
Hey.
Tom. Um, Not specific to that. I had sort of a different comment, but I'll go ahead. And yeah, first of all, I didn't realize that you were going to be giving this presentation today. So the backstory there is that I started a LinkedIn debate with Tom yesterday on a maybe related but different topic, but just yeah, just you know, wanted to say that that's nothing personal on my part, and I've definitely enjoyed all of our conversations about this and other topics in various settings. But it actually does kind of relate a little bit because, first of all, this was a great presentation. I just wanted to say, I'm like, from my perspective, I'm I'm sort of coming from a place where I'm not like hands-on involved with working with, the tools or the technologies at this point. And one of the things that your presentation, really brought to light is like the degree of complexity in these tools. And so from my standpoint, I think there's obviously, a lot of enhancements and improvements that have come online from VirtualiZarr, Icechunk, and all the various tools. But really, there's a lot of complexity as well. So, and I'll definitely like. I don't know if you've given this presentation in other settings, but I'll make a point to go back and watch it again when I'm able to like fully process it and understand it. But I guess my question or point is just that with all this capability comes a great deal of complexity. So I think it can be a challenge for an organization like ours. For example, I'm with the Integrated Ocean Observing System in NOAA. We manage a lot of ocean forecast model output data, and we are actually actively trying to integrate and incorporate a lot of these tools, and it's difficult. So, from my perspective, I'm kind of maybe asked to make decisions about some of these things, and we have we work with people who are very much more hands-on and involved with these tools and can make really good recommendations, but there's just a lot there. So yeah, I think it's a trade-off. Like, very powerful, very capable, but there's just a lot, in my opinion, a lot more to understand than there has been previously. So yeah, it's a mixed blessing, I guess. But thank you.
Yeah, thanks. I appreciate that. I mean, for other people's context, our discussion was around like to what extent is dealing with this complexity and like cloud nativing the data up front the provider's responsibility versus like a consumer's responsibility. Um, I totally agree that these tools are complicated and not super easy to use. Um, I think that there are ways that we can make this stuff easier in future, and this is still evolving. I think we're kind of here right today. We're at this point where it's like at the forefront, we have this kind of like vision and we have these like foundational layers to do really cool stuff. Like a single Icechunk store that points to a petabyte of data that can evolve live and with ACID transactions is like clearly a very powerful, like low level thing to exist. But but creating those things is a pain and it like requires expertise. And like there are these janky Python tools written by people like me on a weekend, like, and it could be a lot better. It could be a lot easier. Um, and so there's kind of like this debate over what we ideally should do, and there's a debate about like what a data provider can actually realistically do with a finite budget and finite time frame. Um, and those are obviously different things. Um,
Yeah, that's that. Thank you. That's an insight to your discussion. That's something that we all have in mind for sure. I want to leave space for one more question from Christine Smith. Do
yeah,
you
I can
want?
see it.
Yeah.
Yeah, so it's about this filtered subscription thing. Say I've given client A access to certain variables and then client A subscription ends, they still have the manifest and chunk information. Um, it's a very good question. The specific scenario you posit here we don't have a way to end their subscription. We essentially make the subscriptions like addition only. And you're pointing at like a real limitation of the system. Um, Other like more traditional databases that are kind of like serverful and file system based, they would be able to have more granular access controls. But the fact that we are using like object storage as our database puts some limitations. And one of those limitations is that you can't you can make there are you can't make like object storage credentials that have like totally arbitrary permissions. I think you can scope them to prefixes, you can scope them to individual files, but you can't easily be like only these hashed chunks are the ones you're allowed to access, I believe. So I guess it's just like there are like everything in engineering, there are trade-offs, and you've astutely identified one of them with this particular design.
Yeah, I was just curious to make sure I wasn't missing something. We don't at the in Earth Data at NASA we don't have subscriptions, but we do have cases where we have private data, or
Yeah,
we might be like moving to a new version and we may need to hide the older version or things like that. So it's not quite a subscription, but just sort of
yeah,
similar idea. So I was just curious. Thank
yeah. I do think it's interesting how there are these like private sector needs which are couched in terms of like selling data and like subscriptions and embargoes and like marketplaces and stuff. And then there are these public sector needs that are couched in terms of like protecting personal data and like embargoing stuff for scientific results and things like this. And it's like from a technical level, there's not necessarily a meaningful distinction between that kind of like commercial problems and the public sector problems, um, which I think is interesting.
Right. We just kind of use different language.
Right, right. And this is exactly the kind of thing that like cloud data lakes as a business model are supposed to solve. Like this is what like Databricks sells to its customers and stuff is like this kind of stuff. Um,
I mean,
like
it's even interesting because, once you have that, I mean, if you're doing security by manifest, it's a little bit security by obscurity because you're not actually preventing people from accessing anything in that area. You're just
yeah,
not telling them what's there. So if they
yeah,
happen to guess, well, they can find it, or if somebody else tells them what's there, then they can access it.
yeah.
So,
So yeah, you're completely on point.
but
So we,
again,
we actually did the maths
no
on
need to
like
keep hitting this.
yeah. We actually did the maths on like how lucky someone would have to be to find a chunk that they didn't pay for in the space of possible keys and things like that. Um, yeah, but you're right. It is that design specifically of the filter subscriptions thing does rely on security by obscurity. We also have to make sure to vendor only get permissions and not list permissions. Because if you vendored list permissions, they would be able to list the chunks that exist. Um, so that was a fun little rabbit hole. But yeah, yeah.
All right. Well, thank you. I think we could probably leave 1 more minute just to say thank you, Tom. This was a great talk, and I think everybody here appreciated it. Uh, yes, if you can in the sometime you can want to share your slides, I think people will appreciate it as well. Um, and yeah, I think that's it for today. I think, and this is probably like also for the next meetings. I think James is here. I think the original idea was to pitch something for ESIP. I'm not sure, James, you want to talk a little bit about that before we can, Aaron, if you want, you can stop the recording. I think this is probably beyond that.